Okay, why don't we get started? If you guys could, can you find last week Friday's notes? It kind of sucked that the schedule so fell that it was a Friday because I didn't have enough time to finish the lesson that I wanted to on Friday. So can we just start with that today? Then we'll take a bit of a break, and then I'd also like to do topic 4 notes. I'd like to try to get as many of the notes as we can out of the way early. There's only 6 in this unit, so at the end of today, if we finish topic 4, we've only got 2 sets of notes left for all of Chem 30. So you're aware.
I don't know how I feel about that.
Yep. So this is about where we finished last day. I want to just do a little informal review before we start, just to let you know about some of the things that we've been working on as a kind of a quick reminder. The first main thing we've been working on is being able to make an ice table. I strongly recommend put some practice in on this. Has anybody tried the worksheet that I posted on the internet? Any luck with that? Has that been okay for being able to do by yourself? Okay. I would definitely recommend put a few practices in on a few of those questions. It'll look something like this. You'll have x plus y will turn into z plus w. Maybe you'll have a couple of coefficients here. Usually you'll be given a value, like say this is 2 moles per liter. This is 3 moles per liter. Usually then, like these ones over here, usually those are 0 because we assume we don't have any to begin with. And then typically I'll have to tell you what something finished at. For example, maybe I tell you that this guy down here finished at 1 mole per liter. Well, how does it get from 0 up to 1 mole per liter? It must have gone up by 1 mole per liter. Which means this one must have also gone up, but these ones must have gone down. That makes sense? And then the logic would be, well, if this one goes up by 1, if I have a 3 sitting in front of this guy right here, this one would go up by 3 moles per liter because of this 3 to 1 ratio. This one right here, though, has a 1 in front of it, so it's going to go down by 1 mole per liter. And this one right here, by virtue of its 2 in front of it, is going to go down by 2 moles per liter. That actually seems unlikely. I don't think that it actually would go down to nothing. If something were to completely react, then it would be quantitative. So maybe I should make this 3 moles per liter to start with, just to change that a bit. And then you do your subtraction. You'd say this is 3 moles per liter. You'd say this is 2 moles per liter. You'd say this is 1 mole per liter. That kind of refresh your memories about how to do an ice table? Okay. Usually the last thing you do then is you'd calculate a Kc value. And so you'd say like 1 to the power of 1 times 3 to the power of 3 divided by 2 to the power of 1 times by 1 to the power of 2. Okay, I went through that lightning fast. Can you guys interpret where the heck all that came from? This 3 right here has a power of 3. This 1 right here has a power of 1, so that's these 2 right here. This 2 has a power of 1, and this 1 has a power of 2. And you'd calculate the Kc value. What good's a Kc value? How is it useful? Well, so far the main ways that it's useful is it'll tell you whether or not you should expect more products or reactants. Is it product or reactant favored, essentially? If it's products favored, what does it mean about that Kc value? Should be greater than 1. Yeah, a larger number, basically. The larger the number, the more products won. The smaller the number, like 0.001, should mean the more reactants maintained. Yes. Sorry. You can't have a negative value, by the way. It wouldn't be possible to have a negative Kc value because you're not working with negative numbers ever. Okay, another reason why a Kc value is useful, and you need to be fairly fluent at practicing this, is if I give you a Kc value, sometimes we have to set up an equation in a table where I tell you the Kc value is, let's say, 0.5, and then perhaps you don't know one of these values. And so what you end up doing is you put x in for a whole bunch of these variables. Hypothetically, that might look like this would go down by 2x, this would go down by 3x, this would go up by 3x, this would go up by x, and you'd have something like this. And I'd say those ones are the most challenging because then you have to work backwards and solve for what x happens to be. And sometimes it involves quadratics, which means that you may need to either use your graphing calculator to solve. You might have to use the quadratic formula. Most of the time you can play a trick where you just square both sides of the equation, but you need to practice a few of those. So That's really a lot of words to describe essentially one skill. I need you to know how to work with an ice skate. So that's one main thing you should do. Second thing we talked about would have been Le Chatelier's principle, which is essentially the concept of how to stress a system to try to create either more or less products. The example that I really like is the Haber process. Germany needed more bombs. It's easy to make nitrate explosives for bombs. You just add nitrogen and hydrogen together and make ammonia. The problem is the percent yield is only like, I don't remember what the exact number was, but I'm going to guess and say the 30% range. So it doesn't produce a whole lot. So if you want to up that percentage, you need to stress the system. So the main ways you can do that are change temperature, change pressure, change volume, change concentration. And typically the way it works is that if you add something to one side of the equation, it shifts to the other side and creates more of the other things instead. If you have a deficit on one side, it shifts back towards the deficit. So that's the second thing you should know. So that takes me to what we talked about on Friday. Now that we've talked a bit about what equilibrium looks like, we now need to shift into talking about acids and bases and how that works. And so today's lesson, topic 4, is going to get more into acids and bases. But before we did that on Friday, we talked about water. So a quick review of water. What's the pH of water? 7. Which means that according to some formulas you would have learned way back in the day, there is actually an H3O plus content. If the pH is 7, your H3O plus content is 1 times 10 to the minus 7 moles per liter. Which then leads to a really common question kids would have at first. Hang on a sec, isn't water neutral? If water is neutral, why is there an acid content in water? Well, it's because water is actually an acid and a base, technically. And it's very rare, it doesn't happen a lot, but water has this ability, 2 times in a billion, to turn into a hydronium ion and a hydroxide. Hey.
When does that?
2 times in a billion.
2 times in a billion.
And then it immediately turns back. What's up?
Did you get my email?
Yes.
Is you okay with that? I didn't talk to you.
Yeah, I'll have to work on that sometime in the afternoon.
Yeah, that's fine.
Yeah,
just
I'll do my
touch
best.
base with Dwayne. There's just you guys are better at filling that out.
I'll do what I can.
Yeah, do you can and all like that.
Okay.
That's why it's work. It's collaboration.
Collaboration. Okay. Okay, so about 2 times in every billion, water has the ability to break up into these ions, but this is where the equilibrium system comes in. Do they stay in this format? Thank goodness, no. All right. We would not exist if that was the case, because we would have no water. Slowly over time, all of our water would turn into hydronium and hydroxide. So I think most people actually kind of intuitively get this concept before we even mention equilibrium. These pieces right here will start turning right back into water. Other waters will turn into these pieces. And if you ever looked, you would see that like 99.99999% of water really is water, but there are actually some ions in it. Does that make sense? Okay. So last week Friday, what I wanted to do for review was review 4 main formulas. One of the formulas is pH equals the negative log of a concentration. pOH equals the negative log of a concentration. Your concentrations are 10 to the minus pH. And that one as well. You guys recall those formulas from grade 11? And then there was one new formula. The new formula is that we can calculate a kW. So a kW essentially is a K value specifically for water. Okay. Does water act as an equilibrium system? Yeah. As odd as it is, you might think it's a liquid, but there's actually more happening there. The equation is right here. This is your equilibrium system. And so we can actually write a K value for the system where you put the products over top of the reactants. And it would look like this. Here's your product. Here's your second product. And we would divide by our reactants. Like that. But actually, that's wrong. Why? Yeah, we don't divide by anything that's either a liquid or a solid. Okay, it has to have a variable concentration. Gases, you can change their concentrations. You just change the size of the container. Aqueous, you can change the concentration of those as well, because that's how much moles is divided in a liter of solvent. But if water's a liquid, we can't actually do that. So this gives you a kW value. Are you waiting on me? Oh. Okay, one more thought here then. We actually should know then the concentrations of hydronium and hydroxide. Since hydronium is a pH of 7 and hydroxide would also be a pH of 7, if you have 1 times 10 to the minus 7 times by another 1 times 10 to the minus 7, we should always know the Kw value for water. It's 1 times 10 to the minus 14. And that's essentially as far as I got last week Friday, is letting you know that we're going to start calculating equilibrium constants for other things. Kw will be for water, and then later this week we're going to talk about Ka and Kb, which hopefully would make sense that a Ka is a constant for an acid and Kb is a constant for a base. So far so good? Okay, so let's catch up to where we stopped Friday then. I believe we did this question here. You got that far? Okay, and did we do this question here?
Yes.
But I don't think we got to this one. Okay, so why don't we catch up right here then? Let's see that we can solve this question here. Let's calculate the hydronium ion concentration, the hydroxide ion concentrations. If you did this, you dissolved 2.6 grams of sodium hydroxide in 500 milliliters of water. Huh. How do you calculate hydronium ion concentrations? What's the way that you calculate that? Well, one of the formulas is you go 10 to the minus pH. Do I have a pH? All right. Well, another way that we can calculate a concentration is we need to find moles and divide it by liters. Fairly confident I have liters. How do I get moles? Yeah. Well, you have a mass number, right? So one of the skills I need you guys to remember is just how to do basic mass molar mass concentration like calculations. If you have 2.6 grams of sodium hydroxide, anybody know sodium hydroxide's molar mass? It is, yeah. It's very nice. It's like 40 right on the dot. So there's 40 grams in a mole. That'll give you how many moles we have. So I got 0.065. So take 0.065 moles, divide by half a liter. I got 0.13 moles per liter. Now I've done this on purpose though here. Moles per liter of what? Of hydronium? Of hydroxide? Of water? Of what? Of the sodium hydroxide. Yeah, this is really important. So my sodium hydroxide concentration is 0.13 moles per liter. Well, if you remember from like where we would have started chemistry 20, sodium hydroxide has the ability to dissociate into Na plus and OH minus. And it should completely do that. So don't worry about equilibrium at this point here, but it should completely dissociate. So that means that you should have 0.13 moles per liter of sodium ions, but you should also have 0.13 moles per liter of hydroxides. That's actually the first thing we were asked to find, right? If I ask you, what is your concentration of hydroxides? You'd say, there it is. Would you have hydroniums, though? Why?
Just the equilibrium of the water.
Of the water, yeah. This was dissolved in water. 2 times in a billion, water can turn into hydronium and hydroxide. So despite this thing being a fairly concentrated base, we're actually going to expect to find some of the H3O plus concentration. All right, well, this is where the newest formula comes in. If we happen to know one of these two things, and we know the equilibrium constant for water, we can find the other. So this is where that new formula came in. The Kw is equal to your hydroxide times by your hydronium. Well, we know what Kw should always be, right? Times 10 to the minus 14. That's a constant. By the way, quick side note, what are the units for Kw? Good, yeah, there aren't any. If your OH minus concentration is 0.13 moles per liter, and we're looking for hydronium, it's really just a quick divide that down to the bottom of the other side kind of thing, right? I got this 7.6923 times 10 to the minus 14. So one more time, is it possible to have hydronium in a base? Yeah, but it's just because water has that ability. Water is actually an equilibrium system. So is that a lot of acid present? No, I mean it's 14 zeros before you start even running numbers. Like it's incredibly not acidic, right? So much so that it's definitely a base. One last thing that we could do, I didn't ask you to do it in this question, but you could be asked to try to calculate a pH. So another formula I need you to memorize, because it's not going to be given to you on your formula sheet, but if you want to calculate a pH, you need to negative log a concentration. So if the question asks for the pH, hopefully you can handle this. I got to 13.11394. So this is a good talking moment. How do you figure out sig digs for a pH? Yeah, essentially the rule is that these two numbers don't count, but it's in front of the decimal place is what doesn't count. So based on sig digs, then we get 2. So with us getting 2 sig digs, the correct answer, if it asked for a pH, would be 13.11. Which hopefully would make sense. Sodium hydroxide you should recognize as a base. What sort of pH does a base have? pHs should have very high numbers if it's a base, right? Well, that's pretty darn high, right? So, I think I pointed out on Friday, on the diploma, it's almost, you can set your watch by it. They're going to ask you a question where they ask you to calculate a pH value and it's numeric response. And I think the reason why they make it numeric response is to catch you at sig digs. Okay, this one right here, you couldn't actually fit into the numeric response bubbles, because obviously it's too big. But if, let's say that the answer was 3.11. Does that make sense? You could fit that in the numeric response blank, but some kids, they might screw up and think that 2 sig digs means 3.1. And then you get it wrong because you screwed up the sig digs. Does that make sense? So make sure you're super careful on that. So far, so good? Okay, let's finish what we didn't get to last day then. So here's my last little bit. We've already mentioned previously, just a little bit, the idea that acids are equilibrium systems. That's what I want to get to here is acid strength. There is a table in your data booklet, which I've referenced a few times. We're slowly but surely using it more. And this table here essentially is a ranking system of how good acids happen to be at ionizing. Okay. One of the things that we would have talked about in grade 11 is the term strong versus weak. So far, I've told you that strong acids, essentially they ionize all the time. And that wasn't a lie. Like, that's not untrue. There are basically 6 known strong acids. But what we didn't talk about previously is that in terms of equilibrium position, if a strong acid, I'll just say strong acid, reacts with water and turns into some stuff, strong acids, basically the equilibrium would look kind of like this. The driving forward equilibrium arrow is much, much stronger than the reverse arrow. And so essentially they happen about 100% of the time. That makes sense? We never used the term equilibrium, though, in the past. But essentially, strong acids don't really exist in the state of equilibrium. The ant going forward totally kicks the butt out of the ant going backwards. Does that make sense? So really, there isn't much equilibrium happening at all. But weak acids are actually considered to be equilibrium systems because a weak acid, when it adds to water, it turns into some stuff. One of this stuff, by the way, would be H2O+. But then it starts turning back again. And depending on how far it gets before it starts like reversing itself, depends on how strong the acid is. And so this table right here is basically a ranking system as to how far the equilibrium system was able to push towards the products before it started turning backwards. The 6 strongest acids are listed at the top. And by the way, I think I pointed this one out. Water is actually at the very bottom because water does function as an acid. Only it does it so rarely, so weakly, that its equilibrium position is at times 10 to the minus 14. These numbers here, which we will work with eventually, I promise, are basically a ranking. That make sense? Okay. So like here's some pictures here. HCl, it's actually a strong acid. It essentially doesn't exist at equilibrium as far as we can tell. It's basically a one-sided arrow. It will completely turn into these two things, and it does not try to turn back the other way. But here, this is acetic acid. Acetic acid only reacts about 1.3% of the time. Essentially, some of this stuff tries to turn into an acid, but then it immediately starts turning back. Hence the whole term weak versus strong. When you were in grade 11, I probably told you a partial lie at some point. I lied about how to tell whether something's a strong or weak acid, and it was based on conductivity. I did that at first because when we first started talking about acids and bases, we haven't gotten to that point yet. But conductivity is actually a good indicator of whether something's strong or weak. These things right here, since it 100% of the time turns into ions, this thing should conduct because it has ions. Whereas this thing right here should probably not conduct because although it shows that ions are being made, there's very few of them present. So conductivity is actually a way to gauge whether something's an acid or a base, but it's not actually the reason why it's an acid or a base. It's more of just the test for it. Okay. Here's a formula that we've kind of already done before then. If you want to find a percent yield, the best way to find a percent yield is to take the actual amount you made, divide by, in theory, what you could have made, and times by 100. Well, for an acid, here's how that would look. What you actually make is the amount of H3O plus that's produced. And the reason why we write this one here is that H3O plus can be easily calculated through a pH. If you just dip the pH meter into a solution, you can find the pH. And if you can find the pH, it'll tell you what your H3O plus concentration is. That makes sense? Well, if you divide that by the original concentration of the acid, that'll find you a percent yield. So I've got 3 last examples, I think, or 2 last examples, and then we'll call this lesson done. So let's try this one here. Let's say that I told you that you worked with acetic acid. And we know that acetic acid usually only ionizes about 1.3% of the time because it's so weak. Could we calculate the hydronium ion concentration? And by extension, could we also calculate the pH and figure out what it should be? So let's write out an equation first. Here's an acid. What do acids try to do in water? You guys remember the word we use? And not dissociate. Dissociate is a word used for ionic compounds. Ionize is the right word. It's the same concept though, just different terminology. So this thing will try to turn into H3O plus. What would the other product have to be then? Well, it's got to be this H right here that's joining up with that. So it's going to be a CH3COO minus. Let me just throw states of matter on here. And I guess one more thing, I should draw the double-sided arrows because it's a weak acid. Well, if we were to make an ice table, and I'm only going to do this once, but if we were to make an ice table, essentially what it's saying is that this right here is 0.100 moles per liter. The initial amount of this would be there. If all of it could react, how much hydronium could you make if all of it reacted? The exact same number, right? Because isn't the ratio going to be like 1 to 1? So like if everything reacted, essentially what would happen is this would go down by 0.1 to give this guy a 0. This guy would start at 0 and it would go up by 0.1 to end up at 0.1. And that is if all of it reacts. Is all of it going to react? No, because with it being an equilibrium system, as soon as it starts forming products, the products are going to restart forming reactants. So if we use that formula I just showed you to find a percentage then, take the amount of hydronium, divide by the amount of the original acid, and times by 100. I don't think I've talked about this yet. Have I mentioned what HA refers to? HA is just a generic term referring to an acid. The A refers to the fact that it's an acid. The H refers to the fact that most acids have hydrogen in it. That makes sense? I can give you a better definition later, but at least for right now, this just refers to like whatever acid you're talking about, whatever acid we work with. All right, so let's solve this thing. If the percent is supposed to be 1.3%, we don't know how much hydronium we're supposed to end up with, but we do know that we were supposed to start with 0.10 times 100. Could you guys solve for H2O plus? How do you rearrange? Well, you're going to have to bring this guy up top over there, and you're going to have to take the 100 and divide it down to the bottom. So like your H3O plus concentration would be 1.3%, I guess, times by the 0.10 moles per liter, but then you're dividing by 100. Anybody else calculate that? Oh. Alright, well, let's say I asked you for the pH. I know that's not what the official question says, but let's say the question will find me the pH. Here's what a lot of students do wrong. A lot of students look at the question and they say, hey, you asked me for a pH, and they take this number right here, and they go negative log of 0.10. And if they do that, negative log of 0.10, they get a pH of 1. But that's totally incorrect, because with it being a weak acid of this initial concentration, not all of it reacts. Hey guys, anybody want breakfast? What do you guys got? You got yogurt, bananas?
Yeah,
Apples?
and
bananas. Anybody else? Thanks, guys. Wait, just to make sure I'm clear here, don't make this mistake. Don't negative log the concentration given to you, because acetic acid does not produce hydronium all of the time. It only produces hydronium 1.3% of the time. That makes sense? So the number that we're going to negative log is going to be this number right here. If we negative log this value, thanks, it's at 2.88. With sig digs, I get 2 sig digs, so it's 2.89. What are the units for pH? Good. That makes sense. I think what you'll find in this unit here is that the calculations are not overly difficult, but there are a lot of very common mistakes you could make. And so you have to be pretty good at knowing all of these acid-base calculations. Most of it is so far is actually reviewed from grade 11. Okay, why don't you guys try this one now? I gave you a pH. I gave you the initial concentration of methanoic acid. Try to find the percent. I don't know why I use the word traction. Must have typoed something here. But like, find the percent yield essentially. Figure out what percentage methanoic acid actually ionizes at. Why don't you guys see that you can do this one before I do? Is this our last example, by the way? Okay. So why don't we finish with this? We'll do this, and we'll take a break, and then we'll do the next set of notes. And then we'll finally be done a good chunk. Yeah. Shoot. It's really strange because it was working this morning.
Give it a sec here. I just rebooted it. That didn't work. Yeah. Okay. Yeah. We're downstairs in Lowry. That's weird because I mean, it was working half hour ago.
yeah, I was working late this morning.
Yeah. Hi. What's methanoic acid? Well, let's draw it. Methanoic acid is going to have one carbon, and it'll have like this sort of group to it. So it's CHCOOH. There, that's methanoic acid. If you add it to water, it's going to turn into H3O plus and HCOO negative. We probably don't need to write the equation for this one here, but I would recommend get in the habit of it. It's a useful place to start. Okay, so we're given the pH, right? So the pH is normally the negative log of the concentration. That's one formula. But that one doesn't help us today, right? So we need the other formula. Yeah, so your H3O plus is 10 to the negative. I'll just write the number in, 2.38. So I got 0.004168, blah, blah, blah. Why is that so low? Didn't we start with 0.10 moles per liter of methanoic acid? Well, it's because methanoic acid is a weak acid. Does much of it actually turn into product? Very little of it does. So to figure this out, essentially what's happened here, and again, don't feel like you have to write this every single time, but it doesn't hurt once in a while, just to kind of remember what we're doing. Essentially what we're doing is an ice table here, where this is 0.100 moles per liter, and it has gone down. This stuff started at 0, and it finally ended up at 0.00416 moles per liter. If I wanted you to, I could ask you to actually calculate that, okay, well, this went up by 0.00416, this one went down by 0.00416. But that's not really necessary to solve this particular question, because all I want to do is figure out the percent yield. We ended up making this much out of a possibility of this much. So just take those two numbers, divide them, and we'll times by 100. Long story short, I got a percentage of 4.1686%. With sig digs, I get 2 sig digs, so 4.2%. So does methanoic acid create products? Yeah, I guess, right? But as soon as it tries to create products, they instinctively turn back into reactants. Hence the whole equilibrium issue. Okay, so a quick summary of that lesson. You need to know fairly fluently how to work with the pH, pOH, H3O plus, and OH minus, those formulas. You should be pretty good at those ones. Plus, you also need to know the KW formula. Okay. Like I said, slowly but surely, we're going to start working on acids and bases as well. So, any questions? Cool. Okay, take a 5-minute break, and then I apologize. It's just I've got another lesson I'm going to do right afterwards. Yeah.
Why is it 4.2? Would it be 4.17?
Based on sig digs, this right here has 2 sig digs. As well, this guy right here has a pH. The 2 doesn't count as a digit, so there's only 2 sig digs right there. So then 4.2, this is not a pH number, this is a percentage. Does that make sense? If this number was a pH number.
Percentage, it does matter.
Yeah.
Number doesn't matter.
Exactly, yeah. So as a percentage, don't change it, right? Like 4.2%, that's your 2 sig digs.
Okay, got it.
Okay. Okay, here's our schedule for the next little while, and I need to walk you guys through some of my reasoning, and then we can change something if you'd like. The thing you might want to change is what we're doing tomorrow. Okay, so let me walk you through why I schedule it like this, and then if you guys want to change it, I'll leave it up to you, but I actually have a reason why I put it on tomorrow's date. Okay. Usually, in my experience, I found that kids quite struggle with the first quiz in elite equilibrium. Okay, and I don't mean for you to, but it's something that takes you a little bit of practice. Okay, and so I really want to do a quiz before we leave for our 4-day long week, and I think that makes sense. But I also want to have a day where we can have a work day to go over it, because this might be the kind of quiz where if history repeats itself, I might want to take just like the first 45 minutes of a class and literally go through the whole thing. Does that make sense? Because of that, obviously, I didn't want to put that quiz on Monday. The topics, by the way, for the quiz are actually supposed to be 1, 2, and 3. Ideally, in the next day in sequence would have been to put this quiz on Monday, but I knew in advance we weren't going to finish lesson 3 on Friday because it's a Friday, so therefore I didn't think it was fair to we couldn't put the quiz today. Does that make sense? Which is why I intended on doing this topic today as kind of like an in-between bit, because of the fact that I don't want to throw the quiz at you when we're not done yet. Okay? But what we talk about next for lesson 4 is not on the quiz. So what we could do then is we can mess around with where the workday goes, but I really would like to make it so that we have the work day the day after the quiz. So my thought process is that we write the quiz tomorrow. If it doesn't go well, don't worry. You get to throw them out on purpose, right? That's why I always give you a few to omit. And then we would take Wednesday and probably take the first half of class actually and go over said quiz. And then after that, we would then start on lesson 5 at some point. Okay. That was my rationale. Now, if you guys want to change it up, we can. The only fear I have then is looking at it is we might not have time to actually, if it goes poorly, to actually go through it as a group together. Does that make sense? So I'm okay with changing that if you guys want to. And I certainly don't mean to freak you out and go like, you're all going to fail. Because that doesn't have to work that way. But just experience tells me that kids usually struggle with this at first. So, thoughts? Change it, keep it.
Keep it.
Should we go to a vote? Okay, who wants to keep it the way it is?
Does that mean we're like going over it and then the lesson?
Yeah, that'd be my plan. Is like this lesson 5 would probably be more towards like the end of Wednesday. Like I still want to go over it, right? That's why I started that way. Okay. Okay, it looks like that's more or less in favor. I don't mean to freak you guys out, so please don't go into this tomorrow feeling like it's going to go horribly wrong. But like I said, experience teaches me that it takes a little while to get used to the theory behind some of this stuff. So if it goes really well, that's awesome. Did I give you guys progress logs? How many did I say you could omit? Did I say 3? I said 2. Okay. Let's change that to 3 then. I don't know why I changed that. So in case tomorrow's quiz goes horribly wrong because you feel ill-prepared for it, I think maybe it's better to approach it like this. Treat tomorrow as though you're throwing it away regardless, and if it goes fantastic, that's awesome. If not, totally treat it as a learning experience, right? And just be prepared to, learn from it, do the best you can, and then we'll plan on taking Wednesday to go over it. Does that work? Just based on the way that things fell, with it being a Friday on Friday and us having a long weekend this weekend, it wasn't the most ideal scenario, but hopefully that works for people. So here's what I want to say. What we talked about today then, going forward from this, not on your test tomorrow. So essentially your test tomorrow is 3 main things. You got to know how to do an ice table. And you're going to want to practice that, okay? You're going to want to know how to do Le Chatelier's principle. And there's a few questions where you have to know how to do some pH, POH type calculations. Okay, so that's essentially the test. It sounds very simple at first, but I don't know, we'll see. So the downside is you probably haven't given you a lot of class time to practice stuff. So okay, so let's talk about this next section here, which is not on your test tomorrow. So don't freak out about this. I want to start with just a review question from something that I would have assessed you on in grade 11. So this would have been a grade 11 test question. Tell me whether these are acidic, basic, neutral, or I don't know. And I don't know is actually a valid answer because for the longest while, chemists were actually unable to predict on paper whether something was an acid or a base, depending on the scenario. So let me see whether this rings a bell from last year. If I give you HNO3, what you might want to do is add it to water. And if you added it to water, you might be able to prove that it becomes H3O plus and NO3 minus. And then you would point out and say, hey, look, I produced hydronium. It's an acid. Is that familiar? And then you just have to ask yourself one more question, though. Is NO3 like something logical? And you'd go, yeah, it's a nitrate. And so you'd say, yeah, this is an acid. Does that sound familiar? Let's try another one. If I gave you CHHOOCCOO, okay, well, this one's a little bit more challenging right off the bat. The first question you might have to ask yourself is it ionic or covalent? No. Yeah, ionic or covalent. That's actually ionic. What do ionic things do? They dissociate. So the first thing you might do is don't actually even add it to water. Dissociate it into pieces. So you break it up into Ca2+, and I should have left way more room here. A HOOCCOO negative. Did I make an acid or a base yet? Not yet. So then, hopefully you recall this, you might take this guy down here, the covalent molecule, the HOOCCOO negative molecule, and we might try ionizing it. So if I ionized it, I could add it to water. And let's try making H3O+. What would the other piece have to be if I tried to make H3O+? Yeah, I guess you'd be pulling this H off right here, so it would be OOCCOO, and that would be a 2 negative. And then you'd have to ask yourself, is that a thing? It is actually, yeah. If you look in the if you look up in the polyatomic table up there, it's a thing. It's an oxalate. So it should not have proved that it's an acid. Here's where things fell apart last year, though. It is sometimes possible to prove that it's both. Let me show you a different equation. HOOCCOO negative. If I try adding it to water, I can also prove that it's a base by taking a hydrogen off the water molecule and making an HOOCCOOH molecule. Now, this one right here, last year at the time, we probably didn't know whether this was actually a valid molecule. But now that I've taught you a few more units, you might be able to recognize what this thing is. This is actually 2 carbons stuck in the middle. One of them goes that way as a carboxylic acid, and the other one does the exact same thing. This molecule here is actually a dicarboxylic acid, and is actually a valid molecule. And so I've actually managed to prove that it's an acid and a base. And this was a huge flaw that we would have had in grade 11, which is that this system, it was called the Bronsted Lowry is what we're about to do. It's called the Arrhenius system. Do you guys remember that word? Arrhenius. The Arrhenius definitions of acids and bases was pretty good, but it had a fatal flaw, is that sometimes you could actually prove that it's both an acid and a base. Today's lesson, my goal is to try to show you how to tell whether something is an acid or a base using a new method of trying to calculate acids and bases. It's called Bronsted-Lowry. So let's start with the notes here. So most of this is actually words. There's actually no calculations in this section, so we don't need to worry about calculators or doing any sort of math. It's mostly a theory lesson. I actually try to show Bronsted-Lowry in grade 11 a little bit. I don't call it this theory, but I do it a little bit already. We call Bronsted-Lowry acid someone who donates a proton. And Bronsted-Lowry base is someone who accepts a proton. I want to just go to just a generic acid here, like say HCl. Here's what you'd have done last year. I would have said take HCl, add water. It'll make H3O plus and Cl minus. A pretty straightforward acid kind of equation. Well, according to Arrhenius, according to Arrhenius, is why it's an acid. Arrhenius said, you are an acid because it makes H3O plus. Arrhenius. And like I said, for most chemicals, that works. But Bronsted and Lowry, 2 scientists who combined for this theory, they had a different suggestion. They figured that something is an acid not because of what it produces, but because of what changes hands. They suggested what's really happening is this HCl is giving a hydrogen from the HCl molecule to the H2O plus. And so they suggested that if someone gives away a proton, the thing that donates the proton is an acid. And it kind of changes the theory a little bit. It's less about what it produces, And it's more based on how the reactants combine with each other. And there's a real elegance to this theory. And here's the reason why. H plus, I've told you this before, right? H plus is a proton because hydrogen has one proton, one electron. If you take off the electron and make it H plus, it's just merely a proton left. Well, it's very similar now to electrochemistry. In electrochemistry, we talk about things that donate and accept electrons, LIOA and GER, that sort of stuff. Well, the elegance of this theory is rather than donating and accepting electrons, we're not talking about protons. See how like the similarities overlap here? And this theory works just as good as Arrhenius' theory, only it's now been able to be used to try to figure out the problem of, well, what happens when something's actually working as both? So by the end of today, or at least in the future, a couple days from now, we should be able to talk about how to solve that whole problem of, is it both? So new definitions. An acid is someone who donates a proton. If you give away your proton, you're an acid. So like say HCl. Does it have a proton to give away? Yeah, it's an acid. H2SO4. Does it have a proton to give away? For sure, you're an acid. OH minus. Does it have a proton to give away? Not so much. But you know what OH minus would be great at doing? Taking a proton. Because what happens if you added an H plus to an OH minus? What would you make? Water. Which explains why OH minus is actually a base, because it likes to take protons. So we actually just need to shift our definitions here then. Think of it as a competition again then. Just like with reducing agents and oxidizing agents, and having like a fight, a tug-of-war for electrons. Now it's not a fight for electrons, it's a fight for protons. It's a fight for single hydrogens. If you're able to steal a hydrogen really well, you're a base. And if you're able to give away your hydrogens really well, you're an acid. Similarly to electrons, if you're able to give away electrons really well, loss of electrons makes you a reducing agent. If you're able to take electrons really well, gain of electrons makes you an oxidizing agent. So it's got overlap there, this theory does. So let's just look at some examples then. This is the one I just did, HCl and water. Hopefully you can visualize here, H is being transferred from this guy to this guy. According to Arrhenius, Arrhenius would have said, this is why you're an acid. Again, he's not wrong. His theory wasn't maybe the best one we can come up with. According to Bronsted and Lowry, the reason why this is an acid right here is because this guy can give his hydrogen away. But it adds to it by saying, if this guy's an acid, he would say, well, this guy's then a base. He'd say that water is a base. Water is accepting the proton as well. This works really well for this reaction right here, ammonia, NH3. NH3 is definitely a base, and we know this because if you test it with a pH meter or a litmus, it clearly proves that it's a base. Well, according to Arrhenius, you'd have to produce OH minus to make it a base. Now, that becomes a huge issue because how does an H3O get an how does an NH3 get an OH out of it? Well, the only theory was that, well, maybe water is involved. And yeah, according to Arrhenius, this still works. Look, you made an OH minus somehow, so like the theory works. But the new theory would be, what if we considered this guy right here to be an H with an OH and have the hydrogen transfer over? Yes, it still makes OH minus, but look, there was a proton changing hands. So the guy who accepts the proton is the base, and the guy who donates the proton is an acid. This is actually a neutralization reaction, which then blows kids' minds because you've always been taught that neutralization produces water. Not anymore. So this is actually acid-base neutralization type equation, but water is actually the acid in this example here, according to the new Bronsted-Lowry theory. Water doesn't actually have to be one of the reactants then. Here's another example of an acid-base neutralization example. Here's H3O+, here's NH3. If you can see visually that one of the hydrogens off of this guy is trading places and going over to this guy, well, pull a hydrogen off this guy, it would be H2O. Add a hydrogen to this guy, it would be NH4+. Well, if the transfer of a hydrogen goes this way, the guy who loses is acid, the guy who gains is a base. Does that make sense? It fundamentally shifts because according to Arrhenius, did we produce H3O or OH minus over here? No. And yet, these guys still were acids and bases. Even though it didn't produce an H3O or an OH minus, they still act as acids and bases together. So essentially, this is the new summary right here. Acids donate, bases accept. So changing that thinking, let me show you some more examples and some more concepts here. The first word I need you to know actually has two words to it. You need to either know the word amphoteric or amphiprotic. And this word actually combines very nicely with a word from the electrochem unit. Do you guys remember the word disproportionation? What does disproportionation mean in electrochem? Essentially, it does both. Disproportionation is something that can gain electrons and lose electrons at the same time. If the same thing does both, it's disproportionating. Well, there's a similar concept in acids and bases. We call it amphiprotic or amphoteric. And essentially, they mean that they can act as an acid or as a base. They have the capacity to do both. The most common amphoteric substance that we're going to start with is actually water. Here, look, water. Water has the ability to lose a proton. I can have this hydrogen right here transfer from this guy right here to that guy right there, and it becomes OH minus. This guy has the ability to lose a proton. But water also has the ability to gain a proton. Here, I can write an equation where the proton goes the other direction, and this guy right here gives up his proton to become the CO3 minus, and water becomes H3O plus. You know that whole issue I was talking about to begin class with, where we don't know necessarily whether it's an acid or a base yet? Well, now we have a word to describe that. If something is both an acid and a base, the word we now use is amphoteric, because it can be both. So if I ask you a question of whether it's an acid, a base, neutral, or both, rather than saying both, say amphoteric, because it means it has the capacity to do both. Okay. So here's more pictures, again, of water doing the exact same thing, but have I made my point sufficiently well? Okay, let's move on then. Okay, another set of terminology I need to talk about. Similar to electrochem, where we had words like oxidizing agent and reducing agent. Leo says GER, those sorts of acronyms. There's more definitions in this unit. The term is called a conjugate acid base. Okay, and it may be just best just to go to the slide that's got the picture on it. Okay. Hopefully you can visually see here that this is acetic acid. I mean, if we were to draw it out, you now hopefully know how to draw it a little bit better. It'll be CH3 to a C to an O to an O to an H. There's acetic acid. Thanks. Well, hopefully you can visually see how this hydrogen right here is going to leave, attach itself to water, and make H3O plus and the base. According to Arrhenius, it is an acid because it made H3O plus. But according to Bronsted Lowry, they said maybe a better definition is that the hydrogen changes hands. Well, the new words I need you to know then is that this guy and this guy right here, I do that really poorly. Maybe the next one's better. But these guys right here are known as a pair. This one right here to this one right here is known as a conjugate pair, where they're very similar, aren't they? The only difference between this one and this one is a proton. So they're called a conjugate acid-base pair. This guy is the conjugate acid, and this guy is the conjugate base. I'll grab the back door too. You actually have the same thing happening right here. These guys right here, the H2O and the H3O plus, they're also known as a conjugate pair because they differ by only one hydrogen in the formula. Only this guy right here is the base.
23rd, can you please come to the office?
Here's where equilibrium comes in. We have double-sided arrows. Because what ends up happening is this acid right here gives its proton to this base right here. And it turns into this stuff right here. But then it goes right back the other way. And so this acid right here gives its proton right back to this base right here, and it turns into this stuff. And there's this never-ending cycle of hydrogens changing hands. It's like a hot potato, essentially. This guy has an extra hydrogen. Gives it to that guy. Turns into this one and that one. Well, then this guy right here has the extra hydrogen. Doesn't want the hydrogen. Gives it away to this guy right here. Turns right back to what it started with. That makes sense? So essentially what's happening in acids and bases is there's an equilibrium going on, but a better definition is that there's hydrogens changing hands. And the more something gives up its hydrogens, the more acidic it is. The more something takes a hydrogen, the more basic it is. Okay, now it's time to talk about the table a bit better. So I've been alluding to this table for quite a while now, if you guys can find it. Essentially what happens here then is it lists conjugate acid-base pairs. So if you guys can find this table here, let's start at the very top here. HClO4 is known as perchloric acid. The reason why it's an acid is that it readily gives away its hydrogen. And if it gives away its hydrogen, it becomes ClO4-. How often does it give away its hydrogen? All the time. It never takes it back. Does that make sense? Which is why these 6 at the very top are known as strong acids. Because there's an extra hydrogen on all of the acid column ones. And in the conjugate base column, there's no hydrogen there. It gives away its hydrogen 100% of the time. And so there actually is no equilibrium on those 6 acids. Does that work so far? But all of the remaining acids are a ranking system as to how often they get their hydrogens back, if that makes sense. So the next strongest acid we have is oxalic acid, HOOCCOOH. And it likes to give away one of its hydrogens. And it's actually pretty good at giving away its hydrogen. Although it's going to come back, it doesn't come back nearly that often. Does that make sense? Like the cat came back the very next day kind of song there. Essentially, someone's going to try to give away a hydrogen. And if it can get rid of the hydrogen and keep the hydrogen gone, it makes you strong, quote unquote. But if the hydrogen starts coming back again in an equilibrium system, it makes you weak. So as you go down this table right here, all the way down at the bottom, like say water, does water try to get rid of a hydrogen? Sure. Because it'll turn into H3O plus and OH minus. But almost instantly, that hydrogen is going to come right back again and remake water. So although water has that ability to, it's not very good at it. Essentially what we can do then is we can actually make this table look the exact same as we did with the equilibrium table. On this side of the table are your acids, and right next to them are the conjugate bases. The strongest acids are up in the top corner going down. These people up here, those top 6, those are your strongest acids because they are good at losing, not their electrons, but losing their protons. Does that make sense? They're good at ditching that hot potato of a proton and getting rid of them entirely. As you go down the list, these things down here, they'll try to lose their protons, but the proton came back the very next day. Does that make sense? Similar concept on bases. The strongest base is actually right down here in this bottom corner, and it actually goes up the other way. What is in that location down there in the bottom corner? Nope, you're looking in the acid column, look in the base column, OH minus. Doesn't that fit with everything you've learned so far about bases? Wouldn't the strongest base be a hydroxide? Because what would a hydroxide want to do? It would love to pick up a proton. Because if hydroxide could pick up a proton, it would become water. Does that make sense? So this table actually functions very similarly to the electrochem table. Your strongest acids going downwards, your strongest bases coming upwards. Does that make sense? Okay. So I talked about this earlier today. HA then is a symbol just for some sort of generic acid. Now I can probably describe it better. The reason why we write it as HA, A is because it's an acid, but H is because it's going to give away a proton. A proton is represented by the letter H. So that's why we often write it as HA, to represent the idea that some acid here is going to give a proton away. Maybe here's a picture analogy here. Think of it as a fight for electrons. Maybe not so much a hot potato concept, but here you've got an acetic acid. It's got a proton on it. And here, this guy right here is going to try to steal the proton. If it's able to steal the proton, then it's a stronger base than it is an acid. So there's actually a similar concept in acids and bases. Remember how in electrochem, if it was like in the right orientation, a spontaneous reaction occurred? And if it was in the other orientation, a non-spontaneous reaction occurred? Well, that actually has the same sort of concept for us. Let me just redraw a new table. Let's say that something up here reacts with something down here. In electrochem, we would call that spontaneous. In our unit, I would say that it's going to be 50%. It's going to be more than 50%. Does that make sense? If something is able to react in this reaction right here, there's going to be a more than 50% yield. It's going to happen a lot. However, if you had something reacting in this sort of orientation, too far. You know how we would call that non-spontaneous? Well, this just means that your percent yield is going to be like, say, 10%. If it was from here to there, that might happen 5% of the time. That makes sense? So the further away these things are on the chart from each other, that actually affects your percent yield. So if you were to have something like, say, here and there, that might occur 99% of the time. If it was here to here, that might happen, say, 60% of the time. And if it was here to there, that might happen 20% of the time. That makes sense? So the placement on the table will actually give you a clue as to how well the yield is going to work. Because it's a fight for protons. Does that make sense? Okay, let's try an example. Hopefully I have one nearby. Okay, let's just flip all the way to the examples, and I'll cover the stuff I skipped in there. Let's kind of figure out what's going to happen if sodium hydroxide gets neutralized by vinegar. You guys find this one? Okay, so what we've got sodium hydroxide. Do you guys know what vinegar is? Good, it's acetic acid, which is CH3COOH. So think of it as kind of similar to our electrochem unit. What sort of stuff do we have present? Well, we have Na+, we have OH- because this thing's ionic, we can dissociate. And then we also have CH3COOH. So in a similar way, let's find out where this stuff is on the table. CH3COOH is an acid, and it's about, you know where the fold of the paper is? It's 2 below the fold. So it's right about here. That's where that one's found. Where's OH- found? Very, very, very bottom. If this were electrochem, would this be spontaneous or non-spontaneous? It's spontaneous, yeah. So I can actually already answer this last question here. Are we going to make reactants or products? Products is the right answer, because this is a fairly spontaneous reaction. This is a very strong base, and this is a mediocrely strong acid. So like there should be, like the reaction should occur. There should be a transfer of protons fairly well. So here's how I'd write the equation then. Your CH3COOH will react with the OH-, and it's going to turn into whatever this guy turns into. So what's the conjugate base of acetic acid? Well, it's the exact same thing, just minus the proton. And it's whatever the hydroxide turns backwards into, which I believe is water, right? If I were to start labeling stuff, where's our acids? That's not on purpose. That guy's an acid. Why? Well, because he gave his proton to that guy right there. Does that make sense? Based on that logic, this guy right here accepted a proton. He's a base. But I said acids. I made sure to emphasize the S. Because although this is going to make a lot of products, maybe 70% yield, I'd expect, it is equilibrium though. That proton is still a hot potato that's going to get passed back again, occasionally. Right? On this side of the equation, who's the acid, who's the base? Yeah, water is the acid. and the acetate's the base. That makes sense? Because what's happening here is this guy's going to pass the hydrogen right back. The only deal here is that before it was able to start reversing the reaction back again, it probably made, I'm guessing here, hypothetically maybe like 70%. I know it's more than 50 though, right? It has to be more than 50 because of their location on the table.
How do you know that the product?
Because of the location. Because this guy and this guy were in like a spontaneous direction.
The opposite way, like they did that.
So let's say that it reacted with something up here. Will it occur? Yeah, but it might only be like a 12% yield. Does that make sense? Now, I don't actually have a way for you to calculate what the yield is, but we can estimate it based on that. Okay, one more thing I should point out here. You're going to like one thing about acid-base reactions, the coefficients. Yeah. And the reason why they're always ones is because you're always transferring one proton, one hydrogen. So you rarely have to worry about balancing these things because you're just moving one proton at a time. Let me try another example. What happens if we take ammonium nitrate fertilizer? Actually, no, it says ammonium nitrate fertilizer is produced. So what it's saying is, what if we take ammonia and nitric acid? What's going to happen? Okay, so do something similar to the electrochem unit. Write out what we've got. We've got ammonia. We've got nitric acid. Find them. Whereabouts on the table are they located? Nitric's way at the top, isn't it? HNO3. It's way the heck up there. It's a strong acid. What do strong acids like to do? Give away their protons. Yeah. Okay, we need to find ammonia. It's like way at the bottom down here. As I look at their placement on the table here, is this a reaction that should have a high percent yield or a low percent yield? I'd say, yeah, very high. Because essentially, and HNO3 really wants to get rid of its proton. And NH3 actually really wants to have a proton. So this is a good scenario here, right? So the way I'd start by writing is saying, well, these two things will add to each other. Okay, the HNO3 is going to turn into its conjugate base. So then look on the table and tell me, well, what does it turn into? Well, it turns into an NO3. The NH3, what does it turn into? NH4 plus, yeah. Okay, let's label these things. Who's the acids, who's the bases? Plural, by the way. Okay, well, this guy right here, the HNO3, it's an acid. Which you probably would have guessed, right? Because HNO3 starts with a hydrogen, right? We call it nitric acid. It's probably an acid, right? Which means that this guy over here is the base. Because the proton is going from one to the other. But here's where we need to bring in the equilibrium system. If it's that hot potato of trying to give away a proton, although it looks like this is going to happen almost all the time, let's call it 99% of the time, once in a while, it's actually going to go back the other way. Does that make sense? I mean, in the same fashion that water 2 times out of a billion can produce an acid and a base, so should this. So it means that we have another acid over here and another base right there. So one of the skills I need you guys to have, not for tomorrow, but in the future, you need to be able to label acids and bases, plural. Sometimes even you need to know the conjugates. The conjugates would be these ones right here are conjugates with each other, and these ones right here are conjugates with each other. So far, so good? No. Let me see whether I skipped anything we should talk about. Okay, well, this slide right here essentially just talks about the whole, if you have acids and bases in the downhill sort of relationship, the reaction is going to occur with like a more than 50% yield. If it happens in this orientation, the reaction will still happen, but it'll have a very low yield. Let me do an example of that, actually. let's just have water react with water. That seems kind of dumb, but let's just say you have a jar of water sitting there. According to this table, where is water located? It's located right down here. It's also somewhere else. Yes, see it, it's right about there as well. So water and water should be able to react to produce, well, this guy over here is going to produce H3O+. This guy down over here is going to produce OH-. So can water react with itself? Yeah. However, in this sort of orientation, will it do it often? No. I mean, and again, you know this number. It does it about 2 parts per billion. But it does have that ability to. Right? But I mean, essentially, as soon as it transfers a proton here, it immediately throws the protons back the other way. So in a way, like you're an acid, you're a base, you're an acid, you're a base. We try to have the proton go from like this guy to that guy. And then as soon as it does that, it goes right back to where it started from. Right? But if you ever took a snapshot in time, you would see these particles right here. According to the Arrhenius theory, then, water is both an acid and a base. But according to the Bronsted-Lowry definition, this kind of changes things up a little bit. It's currently acting as, like, this one right here is an acid because it's losing a proton, and this one right here is acting as a base because it's gaining a proton. So it kind of changes the definition subtly. Okay. Questions? Okay. Later this week, I want to talk about how to start using these numbers that are listed next to the values there. Those are Ka values. We're also going to talk about Kb values. I'm going to put this all together. But for right now, I mean, with 10 minutes left today, you guys basically need to focus on ice tables, focus on knowing Le Chatelier's principle, and be able to do some pH calculations. That's the main goal for tomorrow. Does that work? If I can give advice, try that equilibrium worksheet. And if you want, bring it to me and I'll mark it for you if you want me to look over some questions. Sound good? Right, tomorrow we'll try a quiz. We'll see how it goes. If it goes fantastic, that's super awesome. If it goes really bad, don't worry. We'll take the next day and we'll go over it top to bottom. We might even just go over it top to bottom anyways, just because it's probably worth our time. Okay, cool.